sure they're acidic, but like also they're directly next to a really good electrophile. So like if your Grignard reagent is close enough to steal one of these, it's also close enough to attack this. So it's just gonna do that. I mean, I would bet money that you usually use, like in reality, in the lab, you usually use a little bit of excess Grignard reagent. And like most of that I would assume, like, I don't know, just in case it's not entirely dry or something, because, well, that's how I do chemistry. I don't do Schlinkline things. I go, I shouldn't fully dry it. I tried it for a little bit in the oven, but like not that long, because I really wanted to do the reaction today. So I would probably do it for that reason, but I bet a little bit of the Grignard reagent actually does maybe get protonated by that.
When you say kill the Grignard, do you just mean like it gets protonated?
Yeah, sorry. Kill the Grignard is just gets protonated, because once you protonate a Grignard, you have made an alkane, and I mean, it's kind of synthetically useless. I mean, there might be another like functional group on there, but the part of the functional group that we're naming this after, the Grignard reagent, is just, well, it's gone and it's just a CH now. Yes?
I know we're talking about alpha hydrogens, but where in that like pKa table would the aldehyde hydrogen fall?
Oh, hey, you know what? That is on the, that's on there, and actually, let me do this resonance, and then we're going to, and then I'll demonstrate. We'll look up the pKa, or I'll demonstrate that one. We'll guess what the pKa is, and then I'll look it up. Or you can look it up, because my computer's attached, it's busy. Because that's a really good question. Okay, so, there is a slide on this. So, the reason these guys are acidic is because, get rid of some of this stuff. Is this visible if I write back here? If I just use a little bit? Everybody cool with that? Okay, cool. So, if I take this guy and I add a base, we'll do this. That's a base, that counts. And we deprotonate that guy. Then we make that a longer bond, so it's not like invisible. There. Base. Base takes the hydrogen. Those electrons go live on the carbon, and we have this, right? It's awkward and difficult to fit like lone pair and a negative charge on here. I don't know if I'm supposed to put it like by the lone pair or not, but there's a lone pair on our carbon. It's got a negative charge, right? But hold on a second, because that's right next to something super convenient, right? So, let me use the correct arrow. Resonance arrow, not the reversible reaction arrow. Got started with 2, and now it's got 3. And that still just has its one little lonely hydrogen. So we've got resonance going on here, yeah? So, all right, carbons don't generally like to hang on to a negative charge. But as soon as we steal that hydrogen and force a negative charge on that carbon, it just goes, here, oxygen, you can have it, and then everybody's got a full octet, and we're not even throwing a positive charge on the oxygen, we're throwing a negative charge on the oxygen, so electronegative oxygen is like, yes, awesome, keep me like this, I will live like this. So we get this, which, I don't know, do you put these in brackets? No, I guess you don't have to put these in brackets. So this is why this is so stable, yeah? Let's talk about this one real quick. I'll wait for him to do that a second. This guy. So, looking at this picture, we've got a planar molecule because, well, we've got the carbonyl is planar, right? And then over, this is easier to point because it's still controlled. Over here, these guys, this whole side is planar, right? We've got a tetrahedral carbon right here, a CH3 group, but this, it only has 2 hydrogens now because, well, it's not this, but over here we've got a hydrogen and a carbon, and this whole group of boys here, that's all planar. Because we use p orbitals to do pi bonds, right? So we've got 3 p orbitals, right? We've got one that goes up and down, and then one that goes like that, and then one that goes like that. And so if I'm bonding with something next to me, the one that goes like that does like direct overlap. If you're just using a p orbital to do a direct overlap, you can get a sigma bond out of that. But usually you're just gonna smash that together with an an S and make hybrid orbitals to get your sigma bonds. To get your pi bonds, you don't hybridize, you keep your p orbitals. And that's because one of them goes up like this, like next to perpendicular to the bond that's going on here, and the other one goes this way. So this one here can reach over and have a double bond, and then any resonance that happens has to happen in that plane. So if I've got reaching over in the vertical p orbital, anything down the line that wants to do resonance has to have a p orbital to work with, right? It can't, the one over here can't just start mixing with this one. Because this, that's a triple bond. You've got overlap here for a pi bond, and overlap around here for a pi bond, right? And then it's linear, and then it's a whole thing. But when we have these double bonds, basically we have to make it planar, and all of that has to be, that resonance has to be above and below that plane, yeah, in the p orbitals. So, if we look at this, and we deprotonate that, the bad quotes, because technically a Grignard reagent is a base. That's not even strong enough. I don't know what it would take to deprotonate this, but whatever. Something that wouldn't want to attack that. That's a nice base. Tert-butyllithium? Yeah, tert-butyllithium is usually the go-to. It's similar to a Grignard reagent, like it's basically just a carbanion, but tert-butyllithium is way too sterically hindered to actually do any sort of useful nucleophilic attack. So this is generally our go-to when we need like a really aggressive base, but like if it's also a nucleophile, we'll probably do other things. So if we were to do that, we would have this going on, right? And if we try to resonate that, hold on. This isn't a lone pair next to a double bond. This is a lone pair on a double bond, right? So our geometry here is in the plane. We've got this, and we've got lone pair Mickey Mouse ears, and we've got a carbon here, and we've got CH3, and we've got lone pair Mickey Mouse ears. These are sp2, right? Because we're using one of our p orbitals. This carbon, the p orbital that, okay, I drew it this way. So the p orbital that's coming out of the board is what's doing the reach around and like the hugging, the around the sigma bond overlap. So we've already got coming out of the board the p orbital, this one and this one overlapping. So if we try to put this into a p orbital and change the hybridization of this, it would have to go in the p orbital that goes this way, right? Like that's the only one left. We already have this one as being used. And that one doesn't have anything left to resonate with, right? There's nothing in that plane this way to like do things with, because these are full. So basically what we've got here is the perpendicular p orbitals above and below the plane of our double bonded stuff. They're already in use, so this guy can't resonate with the rest of that, right? It's just sort of stuck over here because you can't put the same electrons, you can't put these electrons in the same orbital that these electrons are in. Otherwise, all of that stuff in general chemistry where we do quantum numbers and like, it's weird and annoying, but there are like quantum numbers and basically you can have like a quantum number for every electron, right? And they've got like a number of indicating whether it's SP or whatever orbital, and then you've got a +1/2 and -1/2 at the bottom because none of them can have the same number, but they've got different spins. So that's how you differentiate them, right? There's only 2 spins, so we already have those in here. We can't put more. Yeah? Does that make sense? So what's the pKa of this? Does somebody have the pKa table? If you have it up, I should be able to find it pretty quickly. If you've already got Canvas up.
Google
Do you
says
have it?
about 17.
No, Google's talking about this.
Here it is.
Ah. Okay. Yeah, 17's right there, but where's... Actually, it's not even on this one. Interesting. Okay. Yeah, pKa 17 can be taken as reference to the acidity value for the alpha hydrogens to a carbonyl group. Sorry, that's 3. Aldehydes, hydrogen does not exert any special effect, which is their way of saying it is one of those really high numbers. But like, I'll look it up because it's just, they don't always, I don't know, most sources aren't gonna like give you an actual number when, or like a range of numbers when they're not acidic enough to matter. And I think it's funny to like, oh, let's look up the pKa and see if it's, you know, around some of the things that can be deprotonated. And then we get things like 50 and we're like, oh. So you have to be really aggressive with it. Gotcha, okay. I think finding those high numbers is funny. But yeah, basically, I can tell tomorrow's definitely going to be finishing this chapter. Not today. It's all right. I'll figure it out. Whatever happens at the exam happens, but the worst that can happen is there's less content in your exam. Okay. Okay. Base catalyzed equilibration of keto and enol tautomers. So, we did, this is just to show the stability of that negative charge. We're going to do that over again, but I'm going to redraw it because we're going to do something like that because the enol form, enol, the way that it's named, sounds like it has what two functional groups? Enol.
Alkene.
And?
Alcohol.
Yeah. So, I hope I don't stain this shirt. I hate my shirts. Because, like, you know, I used to teach with chalk. It was very visible all over me, but also it was chalk. It went away. I'm hoping that doesn't. All right. Base catalyzed tautomerization. Yeah. So, I'm not gonna do colors for these guys at the moment because we're not actually doing. We're not actually doing an attack yet, or at the moment. So, we've got I hate when they do this. Okay, let's see. I'm gonna do this. Yeah, we're gonna do this. Because they have it written out like this. And while sometimes that's useful, you have that, you have it written like that in your notes, in the post-lecture notes that you'll get. So if you would like to see it that way for this one, that's where you can see that. But I like to use this sometimes because it's good to practice seeing this, or at least just in case you're gonna do that. I mean, honestly, there's no rule saying that you can't write write everything out the long way with all of the carbons. It's just that make sure you know how many hydrogens go there, because the way I do it, you have to assume that that I know how many hydrogens are in there. You have to, or at least if you write it like this, I have to assume you know and that you're right, right? And if you draw out like CH3 or CH2, you have to know how many hydrogens because you're telling me, and then I'm not just assuming you know, and then you can actually be wrong. But, I mean, you can draw all of them like that if you want. Okay, I can make the acidic hydrogen. I almost want to make it red because that just feels like, oh, I don't know, you make the main thing red. But maybe we should make it green just because so far red means lots of electron density, and this is like a proton by itself, and that's it. So I guess we'll do that. Yeah? Does that make sense? I don't know. Yes? Cool? Okay. Are we okay with me drawing like this and getting us kind of used to this? Okay, cool. You can always come to office hours and we can do it the other way. So, let's have a base, a nice generic base, and it's going to, boop, steal that hydrogen, and instead of drawing the arrow to the carbon, I'm just gonna skip, and then doing a step of resonance, I'm just gonna skip that and go here. Fold on over there. Oh, that was a really ugly. Just make my fingers all the way blue here. That was really ugly. There. Fold that on over to a double bond. Kick these pi electrons up here. And we get to skip a step. So now we have and double bond here, and this guy's only got 2 hydrogens left, right? Then, oh, and I guess we also have wait, oh, okay, fine, we can make the base negatively charged so that that doesn't help us. Because when our base or our acid is just B or A, we can put whatever charges we want on there. Okay, so this guy is resonance stabilized, right? But we already drew that. And this is the enolate anion. Wait, where am I? Okay, yeah. Sorry, there's the exact same thing is basically on here 3 times because one of them is showing this to here and the resonance, and the next one is showing this to here to the resonance, and then the next step. And so I keep looking up at the thing and like, that's not the rest of this. What are you talking about? Sorry. Okay, so now we've got, actually, let me put this guy in a useful space where I can reach it, because now we've got this protonated base hanging out, and you know what that protonated base can do? Its bases are really good at, well, a protonated base is what? A conjugate acid, right? What are acids good at doing? Giving away protons. And so we can just do this. I'm not going to color that green for now because that's a bond and not a negative. So keto, enol, tautomerization. I don't want to spell it. I might be able to spell it, but I don't want to write it.
So where you wrote enol is so we learn it's an
Yeah, this is
alkene
just,
and an alcohol.
yeah, this was just like enol. Remember when I was like, what does that sound like it has? Enol, en, double bond, all, alcohol.
And then the bond on the O is just 'cause
Yeah,
it's
so
an
this
alcohol.
is,
Okay.
yeah, this is fake. This is just me going, hey, that's what it sounds like. It's like adding them together. That doesn't matter though. What's real is that guy's an enol, that's a ketone. Tautomerization. But you can get it up there because that's